Okay, so today we are going to start digging into core machine learning algorithms. We'll start with a specific class of algorithms called supervised algorithms, which are also referred to as clustering techniques. And I mean, the entire topic of clustering is very, very vast, and there are so many algorithms, and we are going to touch upon a couple of important ones, k-means and document clustering. Okay. Okay, Sanjeev, your question is which statistical methods in which situations and why? Oh, that's a very, very general question, Sanjeev. I don't know if it's, yeah, it's very general, right? I mean, there are hundreds of statistical methods and there are pros and cons for each method. So in the course, we will touch several important methods which fall into different categories of algorithms. That way you get a sense of kind of all classes of algorithms under machine learning umbrella, and hopefully that gives you some flavor as to when you can use certain classes of algorithms. Okay. Okay, great. Okay, so yeah, first we'll look at some common use cases for machine learning. Probably we already talked about several of them in the beginning of the class as we introduce ourselves with data science. But today we'll focus on two classes of algorithms and the related use cases, which are supervised and unsupervised learning. And rest of the class will be totally on supervised learning. And in the next class, we will look at unsupervised techniques. Okay. So Sanjeev, we are just starting, and as I describe each method, I'll also try to focus on when and why to use them. Actually, a lot of methods, as you see the difference, the difference is pretty clear, and you will understand when to use each of this class of technique. Okay, so yeah, just hold on to your curiosity, and hopefully it gets clear. Oops. Okay. Okay, so we briefly talked about this use case already in the first class, I think, which is recommendations in YouTube, right? And the purpose of recommendation is obviously pretty straightforward, right? It's intuitive. Why does YouTube want to recommend videos to you? So that you can spend more time on YouTube and probably look at the advertisements, and or at least once you will click on those advertisements, and there will be some business that is taking place as part of that process. Okay, and also they want to increase the number of videos people watch, and maximize the customer experience in general, right? But primary reason is they want to keep you on that website as long as possible. That's true for any website, right? If you go on Facebook, whatever enhancements, whatever features that they add onto Facebook is essentially to keep you on Facebook as much time as possible. And one corollary to that would be over the time they'll start showing you different ads based on your interests and based on your based on your interest and based on your current needs and so on, right? And through those advertisements, they make business, right? If you look at Google or Facebook, actually Google, more than 70 or 80% of their revenue is totally from advertisements that you see on YouTube, or that you see primarily on Google search pages, as well as on other web pages. Okay, so that's why they want to keep you for a longer time, and the primary method to do that is by recommending you some relevant products. Okay, in terms of YouTube, those products are videos. In terms of Amazon, they are products, real products. And in terms of, in the context of Google, there may be some other products that are relevant to your search queries. So depending on the website, the notion of recommendation changes. Like if you're going on Netflix, they'll recommend you videos, the TV series or the movies, right? So depending on the website, the specific products that they recommend you will be different, but the high-level notion is essentially recommendation. Okay, so that's the underlying machine learning task, and there are many algorithms for it. We'll get to one or two later in the class. Okay, so that's one popular use case, and obviously in YouTube, how would anybody want to? How would YouTube website will start creating recommendations, right? It's primarily based on your history, and that history combines a number of things. Okay, one basic thing is the demographic information. What is your age? What is your gender? What is your location? What is your occupation, and so on, right? And also some interests that you may have listed in a specified manner. Like in Facebook, you will have a lot of likes. So if I go and like a lot of rock bands, then Facebook can understand that I'm interested in rock music. Okay, and similarly in Twitter and other websites, you explicitly give some interest, whether you're interested in sports, music, movies, and so on, right? So that's one class of features based on which they do some analysis. And on top of that, there is a historical data which kind of captures the interactions between you and the website, right? So on YouTube, you will be watching videos day in, day out, right? Every day we'll watch at least one or two videos. And over the time, you can kind of get a sense of what that particular user is interested in, looking at the list of videos that particular user has been watching, right? So these are all the different factors or the features based on which the analytic algorithms will act upon, and they create some kind of a learning model. If in the context of recommendations, it would be a recommendation engine, which will, given a user, it will throw out some recommendations. And if that model is some kind of a prediction model, it will that model will be giving you some yes or no, or spam or not spam kind of output. Okay, so that's one use case, which is about the recommendation engine. And similarly, there's so many other recommendations as well, right? One popular one is wine recommendation. Whenever you go to a store to buy a wine, usually you go online and search for that wine, whatever you're interested in, look for the rating. And those ratings are given by certain companies, certain popular people, and so on. And there are also, actually in the Bay Area here in California, there are a couple of companies which try to come up with some recommendations based on the list of wines that you previously showed interest in. Okay, and it's a big business. That startup company actually raised a few $1 million very recently in the funding round. So And again, in the case of wine recommendation, if you think of it from a machine learning perspective, you have to think about what kind of features you want to include in that problem setting, right? So the core machine learning technique for recommendation may be same across these domains. I mean, obviously you need to add some like domain knowledge into it, but the core algorithm may be same. It just differs in the type of features that you include in that particular model learning, right? So in case of YouTube, you talked about a list of videos that you have seen and the genre from which those videos are taken from. And if it's about movies, maybe it includes the production house, the director, the main actors, and so on. So those are all the features that you can think of in the context of movies. Whereas in the context of wines, those features can be will be completely different, right? It will be about the type of grape and the type of brewery from which the wine is made, or the vineyard, or the year, or the location frame where the grape is coming from, the color of the wine, and the intensity of the wine, the tannins and the oakiness of the wine, and so on. So there are so many features that you can think of, right? Or even most simpler one is how cool that bottle looks like. Most of the time you go to a store, you just pick a wine that is kind of appealing to your eye, right? So all those things matter when you're making recommendations for wines, okay? So the bottom line is the fundamental techniques may be same. It's just that the type of data and the type of features that go into the model building phase will be different depending on the application. Okay? Any questions so far? Okay, Shabarshi has, is collaborative filtering the standard algorithm used in all cases, or does it vary for case-to-case recommendation? So collaborative filtering is a very general idea, and the core algorithm is kind of constant across everything, but typically that wouldn't buy you a lot. So on top of that, you will add your own twists to it. And also, most of the secret sauce for all these machine learning techniques will be in the way you prepare the features for modeling. Okay. So in terms of techniques, yes, collaborative filtering is one of the fundamental one, and probably used in many recommendation engines. But there's always a lot of their own handcrafted solutions on top of that. Yes, we would look at recommendation engines in the context of Mahout in a couple of classes further down. Okay. Okay, and similarly, nowadays, like if we think about the Aadhaar project in India, or if you go to any immigration website, they take your biometrics, right? Fingerprints and scan of your eyes and so on. So what do they do from all of that? First of all, why is it even important, right? So it's pretty straightforward in the context of immigration, because they want to be, they want to provide security. So they want to scan all your information, and based on that, they do some background checks, and whatever you do in the future, they can always relate to your past activity, right? So, so in the context of immigration, it's just national security and the border security and so on. And similarly, you can kind of extend those techniques in the context of banking and financial sectors as well, right? To prevent fraudulent behavior in the system. Okay, so let's take a quick example of a fingerprint. So when you actually go and scan, they just don't scan the entire picture and store it. but instead they scan the picture and then they identify key features in that particular scan, okay, which shows the curviness of the your fingerprint or different markers that are known to be important in the context of fingerprints. So they take all these markers and then they store these markers in their database. So those are the features that describe you as an individual, okay? Now, once you create those features, you can always use it in the context, in conjunction with other information, maybe your demographic information and your, if it's a bank, your financial history and so on. If it's immigration, your travel history, when are you, wherever you are crossing the border or the time at which you are crossing the border. So these are all the different other type of features. So essentially you are bringing your markers that you got from your biometrics along with the other features and then using the entire data in a bigger context of providing security, right? Okay, this is just some more details about it. Maybe we don't need to go into each and everything. We already know about this particular project, very, very massive project in India, right? It's a lot of time, money, and systems to collect all this information for 1.2 billion people and store it and manage it and further down analyze it. Okay. And we can come up with many such scenarios. Basically, this one talks about the paycheck secure system, which essentially monitors different financial transactions across a company or a particular region and so on. Okay, So these are some of the examples where some machine learning techniques can help. But before even going and understanding a particular class of machine learning, so let's even understand what exactly is machine learning, right? So can anybody tell me what do you think is machine learning before we go into the details of it? Does anybody want to come on air and share your thoughts on what machine learning is? Okay, Sanjeev says using incoming data to improve the predictive models. Okay, anyone else? It's one kind of artificial intelligence, Sudhir says. Okay, Partha says it's something learning from the data. And Sanjay says learn based on the past data. Great. So, yes. So each of which actually covers a different flavor of machine learning. But let's first understand the crux of machine learning, right? It's essentially what does a regular algorithm tells you? It just basically tells you a list of steps to massage the data or to kind of create aggregations or create some kind of statistics over the data. If we take an example of face recognition, right? There are two types of techniques that you can think of. Okay, one is in one class of algorithms, you describe what a particular face looks like or what a face looks like, right? You tell your computer program that a face will contain, at least a human face contains 2 eyes, 2 ears, eyebrows, nose, mouth, cheeks, and so on. So you describe all the features that you can think of in order to detect a particular face. Okay, and obviously you have to tell that program how do you represent that particular eye in terms of computer data structures, and then how do you recognize that particular structure in a given image, and some kind of a matching algorithm and so on. But one class of algorithm is basically telling you what a face looks like, and then the program can go ahead and for every incoming image, it flags whether this is a face or not a face based on those features, right? So that program will look in a given image, does it have 2 eyes in this particular shape, and does it have nose between the eyes, and does it have a mouth in a particular shape under the nose? So those kind of matching that will be done by the program, and it will finally tells you yes or no. Okay, that's one class of algorithm. And the other class of algorithms will be, you don't need to tell what a face looks like. You just tell a bunch of examples of faces. You give about 1,000 face pictures to that program, and at the same time you give another 1,000 non-face pictures. Okay, maybe some other pictures, some garden or some other parts of the body or whatever. Okay, so you have provided that particular computer program 2 classes of data. One is all the faces, and the other one is all non-faces. Now it's the responsibility of the computer program to identify the key or salient features of faces which discriminate them against others. Okay, it identifies all those features, and whenever you give it a new picture, it looks at all those features and tells you whether it's a face or not. So in the second class of algorithms, you're not really telling what a face is. The machine itself is learning what that particular face looks like from the example data that you provided. Okay, so in that sense, as Sanjay told here, you are essentially learning based on the past data or some data that you give to that particular program. Okay, and similarly, Partha also kind of captured that notion by saying you are learning from the data. Okay, so in one case, you are giving the list of features to look for, whereas in the second case, you are kind of giving the algorithm a chance to learn from the data. Okay. So Debagna says, so basically it learns from historical data and then applies that learning into the test data. Yes, in a way, you can think of that way. I mean, applying the testing to, applying that learned model to test data is something that kind of varies between different algorithms, because in case of recommendations, that acting upon the model is happens in a way. In case of clustering, it happens in a different way. In case of classification, it happens in a completely different way. So there are 2 parts to any machine learning task, right? One is you have some data and you learn from the data and you build a machine learning model or a statistical model. Okay, that's the first part. And the second part of the problem is how do you use that model in practice? Okay, which is what the second part of what you told Debagna. The using of the model depends on, again, the type of algorithm. If it's a recommendation, that model will provide me the list of YouTube videos that a particular user will be interested in, or a list of wines that a particular wine enthusiast will be interested in, or just a spam or no spam, yes or no kind of class labels that the model will output. Okay. In case of clustering, that using of the model will be completely different. So at high level, the 2 phases of model building and using that model in action is kind of constant across all the machine learning tasks. But depending on the type of the problem, the way you build a model differs, and also the way you use the model also differs. Okay. Now, as we see different algorithms, we will see how to build that model, and at the same time, how do I use that model? Okay. Is that clear? Okay. So Sai Siva asks an interesting question. In YouTube, it uses only metadata, not actually the data. So that actually depends. I mean, you can actually go and mine the data as well. You can take, let's say, images or the frames from different intervals in that video, and then you can do some image processing on those frames that you obtained from the video, and then you can kind of build some features on those images. Or you can take the audio and then convert those audio into different features and then use them into classification model. Okay, maybe that way, or clustering model. Maybe let's say I want to group all the videos based on the type of audio that is there. So that way all the classical music goes into one, all the Carnatic music goes into one cluster, and all the rock music will go into other cluster, and so on. So depending on the problem, you go after the features. Okay. The recommendation probably will be based on the metadata of the users and the videos, but maybe it does something more. We don't know. Okay. And Sudhir says, how accurate can models be? Can they be used for critical applications which need really precise computations and not just approximate appropriate results? So the model accuracy is a very important metric, and depending on the algorithm, there's a different way of measuring the accuracy, and depending on the application, there's a different way of measuring that performance. Need not be just accuracy, but some other performance measures as well. So you'll be surprised. In practice, many of the decisions that you are kind of given are provided by computer algorithms. If you look at stock market, the entire stock market is, there's so many computer programs they're trading, right? Not individual people that are sitting and trading. Most of the trading is done by computer programs. Or if you go to bank and apply for a loan, it's not one person who's sitting and looking at your credit history and your past financial history and making the decision, but actually a computer program that is making the decision. Or if you are in US, you go to a apartment complex and try to rent a place. Okay, the rent that they give you, the rent quote that they offer you is actually generated by the computer program based on the location of the apartment. Does it have a pool view? Does it have a parking view? Is it in the first floor, third floor? All those features it takes into account, and also the demand and supply, how many units are vacant and how many applications are coming in, and so on. And then that program will generate some number, and that's the number that agent will quote you. Okay, so you'll be surprised how many places you are kind of driven by those computer programs. Like if I think about the renting scenario, is that program really doing the best possible thing? Probably not, or probably yes, I don't know. But still, we are affected by the performance of those algorithms. So I guess that kind of gives you a sense, Sudhir. Sai Siva, I don't know what that flash voice is. Sorry, is that a book? Oh, okay. High Frequency Trading non-fiction book. Okay, by Michael Lewis. Sounds interesting. Okay, so does that give you what machine learning is? I hope so. It's essentially just like machine learning algorithm. We are learning what machine learning is from the examples. Okay, so we are mimicking what machine learning does actually. Okay, and there are two important classes of machine learning. By no means these are the only two classes. There are many others, but two important ones are supervised learning and unsupervised learning. Okay, and in this class we will mainly focus on supervised learning, and in the subsequent classes we'll sorry, other way around. In today's class we'll focus on unsupervised learning, and in subsequent classes we'll see examples of supervised learning. Okay, so before we go to a particular algorithm, let's briefly understand what supervised learning is and what unsupervised learning is. In supervised learning, so again, just since both are machine learning algorithms, both of them will learn some model from existing data, historical data. Okay, but the specific problem setting kind of differentiates these two type of techniques. In supervised learning, your training data, that means or the data from which you are learning the model, includes two things. One is the input features, the data features, like we talked about age, gender, the interests, and all the metadata in the context of YouTube and so on. So those are the features from which you are learning the model, and along with those features, you also have some kind of a desired result or the class label. That's what we call it as that particular attribute. It's a desired result for every input record in your data. Okay, so this is a so in the context of face recognition, for example, you have a bunch of features describing the image, as well as the desired result is face or non-face. Okay, so that's the supervised learning setting. You have the features of the data as well as the class label or the result for each of the data record. Okay, and obviously, since we talked about there should be faces as well as there should be non-faces. Otherwise, computer cannot distinguish between the two, right? If you just give that program only the faces, then it does not know what a non-face looks like. So it cannot give you better performance. So you need to give enough examples of faces and enough examples of non-faces so that the model can kind of discriminate between the two. Okay, so that's why in the desired results you have some positive examples as well as negative examples. Okay, and then you build these classification models, and supervised learning essentially a main class of algorithms inside supervised learning are essentially for classification between faces and non-faces, between spam and non-spam, between fraudulent and non-fraudulent, and so on. Okay, and obviously you want those models to be able to generalize, meaning whenever a new image comes in, it should be able to predict whether it's a face or non-face, or whether whenever a new loan application comes in, the model should be able to predict whether it should be approved or declined. Whenever a transaction comes in, the model should be able to say whether it's fraudulent or normal. Okay, so that is the meaning of generalization, or the using of the model in the context of new incoming unseen data. Okay, so your model should be able to generalize to the unseen data. So that's exactly what this says. Give the correct results when the new data points are given. based on the a priori knowledge that you build from the training data. Okay, Sanchit, does HFT also involve machine learning? Can you give the full form of HFT? I never heard of that. Is it some kind of Fourier transform or? Oh, high frequency training. Sure, yes, there will be, I mean, I can't call entire high frequency trading as one class of machine learning, but I'm sure there are a bunch of sub problems which can be treated as machine learning. Because even in high frequency trading, you have to, basic thing is you have to decide whether to buy or sell, right? That itself is like a classification problem. Okay. Okay. Any other questions on what supervised learning is? So typically supervised learning, for all practical purposes, you can think of it as classification 1. Sanjeev, what is BOK? Yeah, we'll get there when we look at the actual machine learning algorithm. It's essentially for the way you divide a particular data set into training, testing, and validation sets. We'll get there. Yes, Sudhir, actually there's a lot of data analysis that goes in to, so Sudhir is essentially giving an example, I mean the recent tragedy of Malaysian airline flight accident, and he's saying it would be nice if these models can be used to predict or save such incidents. In fact, there's a lot of data analysis that goes in, like in terms of doing the search process itself, there will be a lot of data analysis, as well as there are a lot of crowdsourcing stuff that happen, which is again kind of data analysis, but done by humans across the world. So, yes. Okay, this is just again the pictorial representation of our supervised learning. So you have your training data, textual data, documents or images or transactions or features about wine bottles and so on. Okay, so you have all that raw data coming in. You do some data preparation and convert each of your data point into a vector, which is called as a feature vector. Okay. And this would be the input to your machine learning algorithm. And since it's supervised, along with the data, you need some kind of a desired result as well, right? Which we called it as class label. Okay. So it takes the data, which are feature vectors, and the labels, and then builds a machine learning model or a classification model. Okay. Or the predictive model, because it's able to predict based for the newly incoming data. Okay, you use that model on the incoming new data, and then you predict what that label should be. Okay, just like you converted raw data into feature vector, here also whenever a new data record comes into your system, you apply those transformations again and then convert into feature vector, and then you give that feature vector to this particular model. Okay, so in the entire picture, there are three main components, right? One is the data preparation or the data transformations, which converts raw data into feature vectors. And the second one is a machine learning model, which takes feature vectors and labels and produces a model. And the third one is the actual prediction, which is using the model in action. Okay. Out of these three, which one do you think is the most important one? Data preparation, model building, and using of the model. Out of these three different tasks, which one do you think is the most important in practice? Okay, there are multiple answers, but most of you answered correctly. It is data preparation. People say 80% of the time goes into data preparation. Model building, it's just too, data preparation is challenging in multiple facets. One is you need to handle this raw data and then create programs that can act upon that raw data, because there's no particular format to it. You need to come up with some pre-processing programs depending on the type of data that you have. Okay, and also that's the place where your secret sauce goes into most of the time. Okay, the new type of features that you extract from the data. And the machine learning model, it's also important, but people spend less time in creating those machine learning algorithms. Okay, usually you start with some well-known techniques and then you build upon that. So the entire, if you look at the entire life cycle, the amount of time spent in machine model building phase would be less. Okay, and using of the model is typically the least time consuming one in terms of the human effort. Yeah, so most of the time is spent in data preparation. Okay, Shabarshi says, does images get converted into binary form during data preparation? So it depends on the machine learning algorithm. If it's a simple classification model, yes, you need to extract some features out of that image, maybe some color information or the gradient information or any other features that you can extract from those images. But if you apply, let's say, a standard image processing kind of algorithms, then they can operate on the image on the whole itself. Okay, even that operation will be on some binary representation of the data, but you are treating the image as a bunch of pixels next to each other. Each pixel will have RGB component and so on. It's not like you extract one or two features and then feed it into an algorithm. So it depends on the algorithm. Okay, so that's about the supervised learning. Now, next class is the unsupervised learning. So it's pretty much exactly same as supervised learning, except that you don't have label information or you don't have the desired result for each record. Okay, so this model is not provided with the correct results during the training phase. Training phase is same as model building phase. Okay, and typically you use unsupervised learning techniques to understand the structure in the given data, underlying structure that is present in the data. Okay, so you're just given a bunch of data points and you want to understand the structurally how your data points are organized. Okay, so in other ways you can call it as a clustering problem. You want to find the underlying clusters which kind of groups different points together. Okay, so that's why unsupervised learning is kind of synonymous to clustering, and supervised learning is synonymous to classification. Okay. One is learning from the examples based on the desired result, and the other one is simply trying to identify the structure that is present in the data. There are several other techniques as well, but clustering is the primary algorithm that is considered as unsupervised learning. So clustering is not really a particular algorithm, right? It's more of a notion. It's a concept. So that concept of clustering can be considered as synonymous to unsupervised learning. But under that concept, there are many other algorithms. Yes. So as you, Partha, your point is completely valid. So this concept of supervised, unsupervised is depending on the label information, but you can always kind of merge these two based on the application. So sometimes I can find the clusters and then use them to build some classification models further down. Okay. And similarly, later on, we'll see something called association rule mining, which is like data mining algorithms. And there also you can use it for classification, you can use it for clustering, and so on. So you can kind of intermix these two, but the primary idea is where in one case you have label information, in the other case you do not have label information. Okay. Debagna, yes, what is your question? Oh, so what's the difference between classification and clustering? So as I mentioned, classification is kind of supervised learning where you have the data, the features as well as the label, whereas in unsupervised learning, you just have features, there's no label. Like if you take example of face recognition, right? In one case, along with the images, you are also telling which image is face, which image is non-face. That is supervised learning or classification. And in the other case, you're just giving bunch of images, that's all. The algorithm will try to kind of group certain images into one cluster and other images into other cluster, and hopefully one cluster kind of signifies faces and the other cluster signifies non-faces, but the user does not say that this image is a face and this image is not a face. Okay, so that's the difference. Any questions? So here you can see similar to previous example, but you don't have the label information here. You directly have raw data, you convert feature vector, you feed it into machine learning algorithm for doing unsupervised learning, and it creates a model. And then you can use that model on the new data and say that, okay, this new data is likely to belong to cluster number 5. Or this one belongs to cluster number 7. So those kind of things that you can do in the model in action phase. Experimental learning. I don't know what you mean by experimental learning, Sanjeev. It's essentially to understand the structure that is present in the data. Oh, experiential. Still, I don't know what you mean by that. You are getting. Do you want to come on air? Yeah, sure. Yeah, go ahead, Sanjay.
Hi, Shiraz. Thanks. This was just a tongue-in-cheek comment. We as human beings, or especially little babies and kids, we learn based on our experiences. Meaning, as the new data is coming in, as you know, they learn from it. Then we go to school and have supervised learning, right? Before that, the way we learn, or you know, or some people learn swimming is by jumping into the water. That's what I meant by experiential learning.
Oh, okay. I mean, entire machine learning can be called as experiential, right?
Yeah,
not just supervised or unsupervised.
So supervised is like going to school, right? You are actually telling what is right and what is wrong. In unsupervised, you are just learning from the new data points coming from the experience or whatever. You know what I mean?
Right, but I mean, everything is based on experience, right? Even in swimming, you jump into the pool, but you learn what is right move and what is a wrong move. So you can kind of force a supervised setting in there as well. But in general, the example of kids learning, for example, it's totally machine learning, and there are multiple flavors of machine learning in there.
Right, it's okay. I was just, it was kind of a generic comment.
Yeah. But the key point is experience is really applicable in the context of machine learning. You're learning from your experiences. That's for true.
Right, thanks.
Yep, thank you. Okay, Sudhir says, do you have any specific example of statistical properties? I assume we cannot use statistical properties in supervised learning. Is it valid? Not really. Some of the models build upon statistical properties that are computed from the data. So I don't know where you got that idea from, but it's not valid. I mean, statistics are involved in all classes of algorithms. Okay, so this is just another pictorial representation of unsupervised learning. You just have a bunch of fruits here, and the machine is going to tell you or group certain items into different categories, and hopefully they will be the correct categories. All the apples will go into one, all the grapes into other cluster, and so on. Right? I'm saying hopefully because that really depends. I mean, the accuracy of your clustering or the result depends on the type of features that you incorporate here. Right? If I simply take each fruit and create a feature vector that contains let's say the size of the fruit, weight of the fruit, and the taste of the fruit. Okay, just with those features, those three features, probably my grouping will not be correct, right? On top of it, probably I have to say what is the length of the fruit, what is the color of the fruit, and whatever other information that discriminates one from each other. Okay, that's why the data preparation or the creating of the feature vectors is highly critical. Okay, if your data does not have enough meat in it, enough things to discriminate between different groups, then you won't get the good result. Okay, does that make it clear? Okay, so quick question: in machine learning, systems learn from exactly the experience that Sanjay was talking, right? Machine learning systems will learn from data, obviously, not the logic. And data is basically the representation of the experience. Okay, that's pretty easy. Okay, so now let's go into more core concept of what is clustering and how do we do clustering. Okay, so what is clustering? I mean, intuitively we can define it, right? You have a bunch of data points and you want to organize those data points into clusters, and cluster is basically a bunch of points that are highly similar to each other. Okay, So you want to keep all the similar items, all the similar data points into one cluster, and similarly you want to keep them far away from all the points that are dissimilar to these points. Okay. So you have two notions. One is intra-cluster similarity. That means a similarity among the items or the data points within that particular cluster, and that should be very high, right? Intuitively. Only then you can say that, okay, all the similar items are placed in one cluster. And in the same context, along with that, you have the notion of inter-cluster similarity. That means if I have 2 points and they belong to 2 different clusters, and the similarity between them should be very, very low. Okay, so these 2 points essentially capturing the notion that the defined clusters are kind of far away from each other, and at the same time within the cluster they are closely knit together. Okay, so for any clustering algorithm, the goal is to have high intra-cluster similarity and low inter-cluster similarity. Okay, so essentially what this gives you is the natural groupings that are present in the data. Okay, and why do we want to do it? It's essentially to understand the underlying structure. Okay, so if I am a supermarket, I have bunch of transactions that are made by my consumers or customers. Now, by clustering those transactions, I can kind of group different segments of my customers. One segment of customers probably buy high profit items like wines and more delicacies. And other group of people probably spend most of their money in regular groceries. And other group of clusters may be spending more on low profit items and so on. Okay, so that's one way of understanding my data. Okay, similarly, and why do I want to do that? If I want to come up with some kind of a marketing strategy, I need to go to a particular group of people and target that marketing strategy, right? Let's say if I have a promotion on wine, okay, very high-end wine, I want to give some promotions. Obviously, I can't take that promotion and give it to a person who spends most of his money in just buying milk, bread, and regular staple food, right? Because he's not interested in it, or probably he's not financially capable enough to spend money on those high-end items. And obviously, it's of no use to give that particular recommendation or the offering to that particular customer, right? So before you come up with your marketing strategy, you need to know what segment of people that you want to target, right? And those segments are essentially given by your clustering algorithm. Okay, so that's one obvious example where you want to understand the underlying clustering structure or the grouping structure that is present in your data. Okay. Okay, so these are many other examples, right? One we talked about is market segmentation, or you want to summarize your news articles. If you go on any of, let's say, Google News, right? That's a classic example of clustering, document clustering. You have a bunch of articles, and the Google News kind of groups them into different clusters, sports, politics, and health, and so on. Okay, so that's summarization of news. And similarly, you can talk about clustering genes information and clustering any other medical trial informations and so on. Okay, and in general, by doing clustering, you can just get some knowledge from the data. What is a structure? or can you come up with some kind of rules capturing the notion of these clusters? Okay, we don't need to go into that, to go into the example. So yeah, this we already talked. Okay, so in clustering, the feature vectors are essentially kind of called as vectors as well. And so this is like a fundamental mathematical concept that we all learned in, I don't know, 8th grade or 7th grade or 9th grade, somewhere during that time. So vector is essentially a quantity or quantity that has two properties. One is magnitude and the other one is dimension. Okay. And essentially it's represented as a bunch of numbers across different dimensions in the data, right? If I have 2-dimensional data, my vector is defined by x and y coordinates. And if I have 3-dimensional data, my vector is defined by x, y, and z coordinates, and so on. And I can have a multi-dimensional space, and the vector will be defined by some coordinates from each of those dimensions. Okay? And that vector will, so if you assume this to be 0, 0, right, in the 2-dimensional coordinate space, this is a 0, 0 point. And if I talk about this particular point, you can kind of draw a vector connecting my origin to this point. So that vector will have some dimension, some magnitude, and the direction. Okay, magnitude will be defined by the length of that vector, and the direction will be defined by the angle of that vector according from the x-axis or the y-axis. Okay. So, I mean, it's vector is introduced here because typically the data is represented as vectors, and later in the class we'll talk about angles and directions. So that's why it's kind of introduced, but don't worry, even if you don't follow completely. Okay, Sanjeev is still not clear between clustering and classification. So, okay, let me unmute you and then we can talk. Hi, Sanjeev.
Hi, no, I don't, in the middle of this, I don't want to discuss this or anything. I just that conceptually, clustering and classification kind of sound about the same, that there's a bunch of population and you're trying to classify the groups within it. So they sound similar. So I would like to understand the difference, but we don't have to do it now.
Yeah, let's take it at the end of the class.
Sure.
Okay. Yeah. Okay. So in the clustering, like in this slide, we mentioned that we want high intra-cluster similarity and then low inter-cluster similarity, right? So the obvious question is, what is similarity, right? How do I define similarity in my problem setting? If I just have a bunch of faces, how do I define similarity between them? Or if I have a bunch of transactions given by made by multiple of my customers, how do I create the similarity? How do I define the similarity between those transactions? Okay. So you need the notion of measuring that similarity. And there are two important aspects in which you can measure that similarity. You can either measure the similarity by correlation, or in the opposite way, you can measure the similarity in terms of distance. Okay, how far they are, how far the 2 points are in the space. And this one is how kind of measuring the correlation, which is essentially like a similarity measure. And there are a number of measures that you can apply, which again depends on the exact problem setting. You choose one over the other. Okay, so popular distance measures, most common one, which we already knew again from I don't know, 7th standard or 8th standard, is Euclidean distance. If I have 2 points in the space, the Euclidean distance is basically the length of the line that is connecting those 2 points. Okay, and similarly, there is a notion of Manhattan distance, also called block distance. We'll see what that is. And cosine distance, which is typically used in the context of document clustering. And there are other measures like Tanimoto distance and squared Euclidean distance and many other flavors of it. Okay, so Euclidean distance, as we just said, this is a popular measure, and we already learned this particular one, which is just given 2 vectors. So given 2 data points represented as a vector. Okay, so we just said in a 2-dimensional space, my vector will have x and y coordinates, so 2 coordinates. And in a 3-dimensional space, I have 3 coordinates. And then similarly, in an n-dimensional space, I'll have n coordinates. A1 to an is my 1 point, and the second point is b1 to bn. And the distance between the 2 is computed this way. You take the difference between each coordinate, square it up, sum, and then take a square root. Okay, that's your Euclidean distance. And pictorially, that would be the distance or the length of the line that connects those 2 points in that n-dimensional space. Okay. And the squared Euclidean distance is exactly the same without the square root. Typically, both of them kind of interchangeable. You will use one over the other. You will get pretty much the same result. Okay. So Manhattan distance is you use if you have a lot of categorical data, but the way to use it is essentially you take the absolute difference between individual coordinates. Okay, and it's also called as okay. The reason why it's called Manhattan distance is Manhattan City in New York. All the roads are essentially like blocks, like in Chandigarh, which is the only planned city in India, right? All the roads are basically parallel to each other and perpendicular to each other. So it's kind of a grid. Okay. Now, if you want to go from anywhere to any other point, the route that you follow will be like a block distance. Essentially, the number of blocks that you need to travel to go from one point to the other. And that's why it's called block distance or Manhattan distance. So if I'm here, I want to go to this particular block, I just go this way, and the number of blocks I crossed is 1. And similarly, if I want to go from here to here, there's no diagonal space because everything is block structured and the grid structure. So I go from here to here and then here to here, or the other way. Okay, so I will be crossing 2 blocks. So my distance is 2 blocks. My distance is 2. Okay. Similarly, from here, from this corner to this corner, my distance will be 1, 2, 3, 4. Okay. And similarly, I can come this way also. 1, 2, 3, 4. There are many ways of going from my lower left corner to upper right corner. But the Manhattan distance will be 4. Okay. So that's the Manhattan distance. Yeah, we just talked about this one. So if I have 2 points in my 2-dimensional space, 2, 2 and 6, 6. Okay. The Euclidean distance will be just the length of the line that is connecting these 2 points, which is if you put them in the equation, you get 5.65 as the Euclidean distance. Okay. square root of 6 minus 2 whole square plus 6 minus 2 whole square. Okay. Whereas in the Manhattan distance, you can't just go in a diagonal manner. You have to go block by block. Okay, that way. And the total distance or the length or the number of blocks that you need to cross will be equal to 8 in this particular case, which is exactly same as 6 minus 2 plus 6 minus 2, which is this equation. Okay, any questions? We are just looking at different distance measures that you can use in the context of k-means. So Sanjay asks a very important question. Does Euclidean distance calculation require all data elements at the same scale in terms of units of measure? If not, how do I normalize the data to the same scale? So again, that depends on the distance measure, but for example, if it's a Euclidean distance, you don't really need to have everything in the same scale, because the difference that you take, A1 minus B1, A2 minus B2, it's between the corresponding entries, corresponding dimensions, right? So there's nothing that you're not taking the difference between two different dimensions. So if A1 and B1 belong to the same kind of unit of measure, and therefore the difference will be defined there. And similarly, A2 and B2 are defined on the same unit of measure, and therefore A2 minus B2 is also defined properly. Okay, so for Euclidean distance, you don't really need to normalize. However, there's a subtle point, which is, let's say if A1 and B1 are measured in terms of kilometers, and A2 and B2 are measured in terms of centimeters. Okay, so the units are kind of same between A1, B1 and A2, B2. However, the magnitude is different. Okay, typically when I'm talking about kilometers, the numbers will be smaller than those numbers where I represent them as centimeters, right? So the magnitude of centimeter values will be much, much higher than magnitude of my kilometers. And therefore, when you take the difference, square them up and sum them up, the difference that the kilometer values are giving you may not be kind of maybe too small compared to the differences that are given by your centimeter dimension. Okay, is that clear? So unit of measure is not the main issue, but the magnitude of numbers may create a problem if you do not normalize. Okay, so Mohan asks, when do we use each of these measures, Euclidean, Manhattan, and cosine? So Euclidean is the most simplest case. Typically, whatever data you have, you just apply that Euclidean measure and see what you get. But in some domains, you use cosine similarity, like when you're measuring the similarity between two documents, then you use cosine similarity as opposed to Euclidean distance. And similarly, cosine similarity will be used, or cosine distance is used in the context of bioinformatic data as well. So, so there's different, I mean, there's no clear answer to it. It's not like a yes or no kind of an answer, but based on experience, typically in document clustering, you use cosine similarity in like a market segmentation or financial data, those kind of things, you use Euclidean. Okay, we'll get to how to normalize the data. Actually, I mean, normalizing the data is pretty simple. You basically, a simplest normalization is you take the sum of all the coordinates and divide that sum from each of the coordinates. So in a 2 coordinate case where I have x and y, I'll divide x divided by x plus y and then y divided by x plus y. That's one simplest normalization that I can do. Okay. And then the cosine distance equation is this. Essentially, what this equation tells you is the angle between the 2 vectors. Okay. So we said each of my data point is like a vector, right? If I go back to my picture. Okay. So let's say I have these 2 points, point 1 and point 2. Now the cosine similarity between the two is the angle between the 2 vectors. So imagine there's a line from here, origin, to this point, and another line from here to this point. The angle between the 2 lines is essentially cosine similarity. Okay. So if I have a point here and a point here, the cosine similarity between the 2 points is essentially this angle theta. Okay. When we come to the document clustering case, we will see exactly what the theta is and how to compute. But for now, just understand that cosine similarity is the angle between the 2 vectors. Okay. So this, the right side component is the angle between the 2 vectors, also called as cosine similarity. But here we are talking about cosine distance. So that's why we said 1 minus similarity. So that similarity value varies between 0 and 1. Okay. And the distance is the opposite of it, right? So whatever is highly similar in terms of distance, the distance will be small. And that's why we took a 1 minus and we get a cosine distance. Okay. So similarity and distance are kind of opposite to each other. If you have values between 0 and 1, whenever you do 1 minus, you get the opposite of it. Rajiv, yes, those Frobenius distance and Mahalanobis distance, I mean, some of them are scale invariant, but maybe not many people know about them. So let's keep them aside for now. Frobenius distance, or one variant of it, is also Mahalanobis distance. Is kind of variant of Euclidean distance, right? It's more generalized versions of that. Okay, and similarly, there is another distance called Tanimoto distance, and so many others, like Rajiv was suggesting. But that's the fundamental of fundamentals that we need to know before we come to any clustering algorithm, right? We need some notion of distance measure or some notion of similarity measure, using which we can apply any clustering algorithm. And one most popular algorithm is K-means algorithm. Okay. Okay, Sanjay, when is similarity by correlation used? Again, it totally depends on the application. I mean, basically, wherever you can use similarity, you can also use distance, because they are two opposite notions of the same thing. But it really depends on the application, whatever is the whatever makes most sense there. Okay, so let's go into K-means. Guys, since we are kind of running slow, I'll you can type in your questions, but I won't answer those questions until I reach a logical conclusion of k-means. So let me kind of go into the details. I mean, whenever I say, do you have any questions, you can kind of, that's the point where I want you to kind of acknowledge that you are following what I'm saying. But whatever questions you have, you can type it in. I'll take it little later into the class, okay? Since we are kind of moving slow. Okay, so let's see what k-means clustering is. So the goal is simple, right? Just like what we said for clustering, we want all the data points within one cluster to be highly similar, and the data points across the cluster to be highly dissimilar. Okay, so in this particular picture, if I have total population, I want to divide into multiple groups, and the objects in one group should be as similar as possible, but at the same time there should be as much bigger distance as possible between the items in group 1 and group 2. Okay, that's just in general the goal of clustering, right? Not just k-means, any clustering. And here this is just example of clusters in the context of some financial data, which has two features. Current balance as well as the gross monthly income. Okay, so I have a bunch of people in my data set, and for every person I have these two attributes that I got from the data, and I can plot it in my two-dimensional space, and I can see that there are two clusters in this particular picture. This cluster is essentially defining a class of customers who has high balance and low income. Okay, so these are more probably people who kind of wants to save more money and plan for future or whatnot. Okay, whereas the other class of customers are high income and low balance. So they want to spend as and when they get money, they want to probably spend. Okay. So these are kind of two different classes of customers that you can kind of uncover from your data. Okay, so when you actually look at your raw data, you probably don't realize that these are the two classes of customers that can exist in your data set. But once you do some clustering and look at your results, then you know that, okay, these are the two classes of customers, and basically based depending on the type of business policy or the strategy that you're coming up with, you can target to one of these customers. Or based on these clusters, you can come up with a different policy. So either way, right? Okay, so let's see what exactly k-means is at a very, very high level. So you have a bunch of points. All these colored circles or colored points are your data points in your data set. And you start with initial k centers. Okay, in k means k is the parameter to that algorithm, and that defines the number of groups or the number of clusters that you would like to produce. Okay, so if I give you some data set and ask you to create 3 groups out of it, then my k is equal to 3. Okay, if I say create 5 groups, then my k equal to 5. So the k is input to the algorithm. Okay, so you randomly select, if I want to say k equal to 3. Okay, I randomly select 3 points in the space, and I'll say these are my initial centers or initial means. Okay, they may be randomly generated, they may be generated in a more intelligent manner. We'll get to those starting point issues, but let's say we randomly generated 3 points and we call them as clusters. So in this picture, we have 4 clusters, actually 4 centers. So your circles are your data points, and these little star points are your centers. So these are the 4 centers that you randomly chose, let's say. Okay. Now, in the next step, you basically compute the distance between every point and all the k centers that you have. Okay. In this case, we have 4 centers. So for every data point, let's say we start with this point, we compute 4 distances between this point and all the centers. Okay. So since we have 4 centers, we get 4 distances for this point. And then we take the minimum because we want to assign that point to the closest center. Okay, so we take this point, we compute 4 distances between all the centers and take the minimum and say that this cluster, this point belongs to this cluster because this is the closest center, the green one. We call it as a green point. Okay. Similarly, I take this point and compute 4 distances between this and the pink, this and the brown, this and the red, this and the green. And when you take the minimum, pictorially it turns out to be pink center, and therefore I colored this point as pink, and so on. So for every data point, you assign the data point to the closest center. Okay, that's what you are saying here by associating every observation or every data point with the nearest mean or nearest center. Okay, so at that point in time, you have 4 centers and you grouped all your data points according to these 4 centers. Okay, and then you update your centers. Remember, you started with some random centers. They can be anywhere in your space, right? You want to update those centers in an iterative manner. And the way to do that is essentially you assign each data point to these centers, and then you update those centers by computing the centroid of each cluster. Okay, so initially we started with these 4 centers, and then we assign each data point to one of these centers. That's how I got these colors, let's say. Now, the third step is essentially to get the centroid of all my data points in one cluster. Okay, I take all the red points and then I compute the centroid. Centroid meaning the mean of all the data points. Okay, I take the average. I take all the x coordinates among these red points and then take the average of those x coordinates. And similarly, I take all the y coordinates of red points, I take the average. I take all the z coordinates of red points and I take the average. Then, so cumulatively, I get average x, average y, and average z. Okay, that would be the centroid of my red cluster. And similarly, for all the green points, I compute the centroid. All the brown points, I compute the centroid. All the pink points, I compute the centroid. So now we have new centers for each of the color. Okay, so probably these guys have moved from here to some other location. Okay, and then you repeat this process. You again compute for every point, compute the distance between that point and all the centers. And then once that allocation of points to different centers is finished, you come to the third stage, which is computing the centroid or the average or the mean, and that's why you call k-means. You compute the mean and then you get the new center. And then you repeat this process again and again. So that iterative process is shown in this slide. So here you started with 4 centers, let's say randomly chosen centers, and then you associated every data point to one of these cluster centers. So even though these points are so far away, you compute distance between this point and all the 4 centers, and you choose the minimum and say that it's closest to pink, so I colored it as pink, and so on. Okay. Once I colored everything, I take the average of all my pink points and compute the new pink center, and that pink center happened to be here. Okay, average of all those pink points. And then I take all the brown points, which are some are here and then some are here. And then I take the average. I get the new brown center, which happened to be here. And similarly, all the red points, take the average, that happened to be this one. All the green points, I take the average, that happened to be here. Okay, so from here to here, I got new cluster centers for all the 4 clusters. Okay, and then again I repeat the process. For every data point, I compute the distance between 4 centers. I take the minimum and I colored it as pink, red, brown, or green. Once the association is complete, I take the centroid, which means I get the new center for every color. So for pink, if I take the centroid, I get centroid to be here. You can pictorially see, right? It's kind of in the middle of all the points. That's why it's average. And similarly, for all the red points, the centroid would be somewhere in the middle, which is happened to be here, and so on. And then once you compute the new centers, you again associate every point to one of the centers, and then keep repeating until you meet certain criteria. Either you reach, let's say, I want to run this for 10 iteration and then I stop, or the movement between this figure to this figure, the movement of clusters centers is minimal, let's say, then I want to move, I want to stop. Okay, so there are a bunch of stopping criteria that can be applied, but you keep repeating until that stopping criteria is met. And at the end of it, you have the cluster centers as well as the association of each point to one of those cluster centers. Okay, that's exactly the output of your k-means algorithm. Okay, so you started with initial data set, value k, that is user given, and then you run this iterative process, and at the end we get the bunch of data points grouped into k centers, grouped around k centers, okay, which are your k clusters. Okay, so that's the high level description of the algorithm. Any questions? Okay, so Rajiv asks, how can we get to know the category or colors beforehand? Did I miss some? Oh, okay, actually that's probably something wrong in the visualization here. So when you started, everything would be, let's say, white points or the black points. Okay. Now I randomly chosen k centers, pink, brown, red, and green. And then I associated every white point to one of these centers, and then that's how the colors came in. Okay. So that picture is missing here. Okay. Is that clear, Rajiv? So initially we don't know where each point is. You randomly chose k centers, and then you chose the closest center for every point, and you colored it that way. Okay, is that clear, Ashwin? Okay, let's see. Okay, Ashwin, let me just repeat that. Let me show you pictorially. That will probably help. Okay, just hold on, guys. Let me take some example data and then. Okay, don't worry about this particular equation statement for now. So I just generated some bunch of data points, XY coordinates. Okay, now let's plot those data points. Okay, initially my data would look something like this. no color anywhere. Everything is blue. I mean, everything is black dots. Okay. Now, if I say k equal to 3, okay, I randomly select 3 points. One, let's say one here, one here, one here. Red, blue, and green. Okay, let's say those 3 are my data points. Actually, let me put that. Save plot as image. Save. Oops. Okay, so this is my data. Now I create a red point here and a blue point here and a green point here. Let's say these are randomly chosen. Okay, my red, blue, and green. So this is how you started off with. Now for every data point, I compute the 3 distances. So I take this data point, compute distance from here to red, here to blue, and here to green. Okay, and obviously red is the closest. So I'll go and say this is my red. Okay, and similarly for this one, I compute all the 3 distances. Whatever is close, I'll say this is blue or green. Let's say this is blue, and so on. Okay, that's how my initial picture came in here. Okay, I started with black. I randomly selected 3 k centers and then colored each of the point based on the nearest center. And then once I allocate everything, I take the average and then I get new centers again. Okay, and then I assign it again. So I get new arrangement. I take average. I get new centers. I assign again. I get new arrangement, and so on. Repeat. Is that clear, Ashwin, now? Okay, great. Okay, Sanjeev asks a question. In figure 1, the pink points are on 2 sides of the page, but in figure 2, they moved together. How and why? Yeah, that's based on the exact distance computations, right? In the initial case, probably this point, for example, whatever is pink here, is closest to pink. But after you compute the average, that means you compute the new center, this point is probably became closer to green than pink. Okay, that's how it got the green color. Okay, so essentially, I mean, conceptually, you are starting with some k random points, and then you are moving those k points according to the structure that is present in the data. And that structure is given by the closest cluster center that we are allocating it to. Okay. So Sudhir asked, just wondering how there are 2 centroids for the same circle. There are no 2 centroids for the same circle. Where do you see that? It's just that here the 2 centers happen to be very close to each other because they are randomly selected points. So, okay, in figure 6, 2 pink centers. Oh, that may be again problem with the way it's shown in your screen, but this is pink, this is brown, this is red, and this is green. Okay, so these 2 are not pink. One is pink, one is brown. Okay, yeah, in this case, k equal to 4. Okay, did I miss any other question? So Sanchit asked what is the criteria of selecting initial k. We'll get there. Well, that's a very, very good question. We'll get to it in a minute. Okay, how do you determine the number of iterations? So typically you don't know the number of iterations. You just think that, oh, okay, 100 may be a good number and I'll run for 100 iterations and see. Or if the movement between the iteration is not much, let's say I already created nice and good clusters, and whatever I do, I get pretty much the same result, right? One iteration after the other. So whenever the movement of clusters between iterations is minimal, then I can stop. So that's another way to provide the stopping criteria. Okay, Debagna asked a very good question. So if I stop after figure 6, okay, let's say I run for 6 iterations and stop, then I can see that pink and brown clusters are very close to each other, right? Pretty much next to each other. So is that a good result? Yeah, if k equal to 4, that is the best result that you can get after 6 iterations. But is k equal to 4 is a good result? Maybe not in this particular case, because it seems like all this should belong to one cluster, right? So maybe k equal to 4 itself is not a good starting point. Maybe I should have only k equal to 3, so that all of this will be one cluster, all of this will be another cluster, all of this will be another cluster. Okay? So again, we'll get to that question in a minute. How do I determine k, whether that result is good or not, and so on. Okay, okay, so, but at this point, I mean, keeping that questions aside, you're all fine with how the k-means clustering algorithm progresses, right? And this is a most fundamental and most popular clustering technique, and it does surprisingly well in many applications. In actually, the first thing that you would want to try on a clustering setting is k-means, and you move to more complicated techniques only if k-means does not give you good result. Okay. So it's very fundamental and it's very useful in practice. Okay, so in cluster analysis, objects are classified into number of groups so that they are as much dissimilar as possible from one group to another group, but as much similar as possible within each group, or they are as much similar as possible from one group to another group, but as much dissimilar as possible within each group. It's pretty straightforward, I think, but let's see what you guys think. Okay, yeah, not surprisingly, option 1, right? You want high intra-cluster similarity and low inter-cluster similarity. Okay? Okay, so before we get to those interesting questions that many of you asked, let's try to little bit understand the math behind it. Okay, so we said that each data point is like a vector, right? So here my data point, or also record, is an n-dimensional vector, right? My xi, the ith point, is represented as xi1, xi2, and xin in an n-dimensional space. And my total data set D is a set of m records or m data points, x1, x2, xi, xm. Okay, and how can I define a cluster in a mathematical terms? Okay, ith cluster, or the cluster to which my ith point belongs to, is essentially what? The closest center, right? I compute distances between my data point and all the cluster centers, and then I choose the minimum. Okay, so that's exactly represented as this equation. I compute the distance between xi and my mu j is Mu's are the K centers, mu1, mu2, mu3 until mu K. Those are the centers. So I compute the distance between my data point and the cluster center, okay, and I choose the minimum, and that would be the cluster to which xi belongs to, okay. Now, with these definitions, I can define this quantity called as distortion, okay. What this means is for each of the data point I equal to 1 to m. Remember, we have m records or m data points. So for each data point, I take the distance between the point and the cluster to which it belongs to. Okay. So we just said Ci is the cluster to which Xi belongs to. Okay. Now I'm taking the distance between the point and the cluster center to which it belongs to. That is the closest distance that you computed. Right? So you take all those closest distances for every data point and you square it up and you sum it up. Okay? This is the distortion that you can define. And for a good clustering, you want this distortion to be as low as possible, right? Because you want every data point to be assigned to closest center. So your Xi minus Ci should be as small as possible across all the different centers, and then you sum it up over all the data points. Okay, and now if you plug in this definition of Ci into this equation, you get something like this. Okay, intuitively, I mean, you can work out the math, but let's understand what this exactly means. Here I have a summation from j equal to 1 to k across all the centers, okay, all the k centers. For each center, I have something called owned by, okay. For given a center, it tells me what are all the points that center is associated with it, okay. So owned by is a set of all records that belong to the specified cluster center, okay. So owned by of mu j will tell me all the data points that belong to jth cluster. Okay. Now I take all those data points, compute the distance between the data point and the cluster center. I sum it up, and then I sum it up across all the clusters. So that's my entire definition of distortion. Now the goal of k-means is to essentially minimize the distortion, right? Because I want all my data points to be allocated to the closest center as possible. Is that clear, everyone? Even if you don't understand the mathematical formulation, if you are fine with the high-level description that we saw before, that's good enough. But I just wanted to give you some math behind it so that you can kind of appreciate the concepts more clearly. Is that clear so far? The definition of distortion? It's essentially the distance between the data point and the cluster center it belongs to. Okay? And your goal is to minimize the distortion, right? You want to find your k centers or your mu j's so that your distortion is minimized. Okay? That's your objective function. Now, okay, that's a find cluster centers that minimizes distortion. Okay. Now, again, from our high school, many of us probably forgotten it, which is if you have an objective function and you want to minimize or maximize, the solution can be found by taking the derivative and making the derivative to 0. Okay. So solution can be found by setting the partial derivative of distortion with respect to each cluster center to 0. So you take the derivative and you equate it to 0, and that's your solution at which you can get the minimum or maximum of the objective function. Okay. So Here I'm taking the distortion and then taking the derivative with the particular cluster center mu j. So my dou of mu j of this entire function is equal to this one. Okay, essentially this is exactly how the derivative operates. This 2 will come here and mu j has minus here, so you have minus 2 and so on. And ultimately when you say equal to 0 and do some math, your mu j is defined as this one. Okay, even if you don't understand your derivative, ignore it. You take derivative equal to 0 and you get this. Okay, so what this means is, if I set mu j to be this value, then my distortion will be minimized. Okay, that's exactly what this says. If I set my mu j, my cluster center, to be this, then I can minimize my objective function distortion. Okay, now let's see what this quantity is. Here I'm taking all the data points belong to that particular cluster mu j. Okay, I'm summing them up and then taking the divide by the number of points in that particular cluster. Okay, so this is exactly like a average of all the points that belong to that cluster, right? Remember, this is exactly how we updated each of our cluster center in every iteration. Okay, now you know why we did it. That is because by taking the average, you are able to minimize our objective function distortion, which is capturing our notion of clustering in the mathematical sense. Okay, so by minimizing distortion, we are saying that we are able to get good cluster, and the only way to minimize in this particular setting is by taking the average of all the data points, and that's exactly what we used in our k-means algorithm. Okay, is that clear, everyone? Any questions? Are you able to kind of appreciate the math behind it, or is it totally over the head transmission? Okay, any yeses, nos? Okay, everyone, somebody please respond. Is that clear? Or basically I wanted to show this so that depending on your interest, I can kind of show the math behind algorithms later on or skip that portion, depending on your preference. Okay, Partha, Rajiv, Nilesh, Manohar. Okay, so good. Yeah, I'll try to show the math without digging too much, and maybe if you don't understand for the first time, you can kind of rewind the video later on and see if you can kind of get your thoughts clear. Okay. Wow, you guys are skipping to the next point before even I go there. People are already asking how is it done in R, and that's exactly what we are going to do next. Okay, before I go there, so Sanju is owned by the, okay, let's show the definition again. owned by is essentially set of all records that belong to the specified cluster center. Okay, in terms of pictures that we have, so owned by of this pink star is equal to the set of all pink points. Okay, the points that belong to that cluster center. And similarly, owned by of the red star is a set of all points belong to that cluster, which is exactly set of all red points. Okay. And you update your clusters by taking the mean, because by taking the mean you can get minimal distortion. Okay, that's why that update rule is applied after every iteration. Okay, let's go back to R and let's work with this example, right? So what I didn't show you before is just some code that generates some random data. Let's not go into it. It essentially just uses this function rnorm. Okay, rnorm. That is a function to generate data from normal distribution or Gaussian distribution. Okay, I just use that function to generate some data, and let's say the data happen to be like this. Okay, my data is that. So if I actually, let me increase the font size. Okay, I can say class of D to know the type of that particular object. Okay, and since it's a matrix, I can say n row of D, which is the number of rows in D and number of columns in D. So I have 100 points from two-dimensional space, and I can say plot of D to simply show the structure, which is what this is. Okay, so that's my plot of D. Now I want to do the clustering, right? So there is a function called k-means. K-means, that's the function that you use in R. Now we already know that by saying question mark, I can look at the help of that particular function, right? Okay, so I can see the help of this function, and as you can see, this k-means function belongs to a package called stats. And stats is a package that gets installed on your machine by default. Whenever you install R, it comes with that package. Okay, so you don't need to say installed R packages. We saw this, right? How do I install a new package? You don't need to do that for this. And similarly, you don't need to load it by calling library. Okay. So you don't need to do anything. It comes with the base packages. So k-means is already available to you as and whenever you open R instance. Now this function takes a bunch of arguments, but the important ones, let's to start with, are your X, which is your data. Okay, that's your numeric matrix of data, and the centers, which is how many centers you want, the K, whether you want 3 centers, 5 centers, 10 centers, and so on. And we said we can provide the max number of iterations up to which you want to run that algorithm. Okay, if you don't provide anything, the default is set to 10, but you can set to whatever value you want. Okay, we'll see how to define how to decide when to stop and when not to stop. We'll see that. But let's just to go and do something. Let's say fit is equal to k-means of D, and let's say I want. Okay, let's go back to this plot. That's my data. Let's say I want to divide into 2 groups. Okay, that's done. So I run my k-means, and I already got the result of k-means with k equal to 2. Okay, now I can again see class of fit. Okay, that's an object called k-means. So it's an object that is produced by k-means, and we also saw a function called summary to see the structure of that particular object, right? Now if I say summary, it gives me a bunch of things. One is a cluster, which is the cluster assignment of each of my data point, and the centers, the 4 center, it should be 2 centers. Okay, let's see, fit dollar centers. Oh, okay, 4 values in it, but it's essentially 2 centers, right? And similarly, there are other things called total sum of squares, within sum of squares, and so on. We'll get to these 4 in a moment. And total 2 centers and the number of iterations and other things. Okay, but the most important one is fit cluster, which tells you the cluster to which each of my data point belongs to. Okay, my first data point belongs to cluster number 2. Second data point belongs to cluster number 2. Third data point belongs to cluster number 1, and so on. Okay, and the actual centers are given by fit dollar centers. These are the actual centers that are found after running k-means. Okay, so that's very simple, right? Now let's see how good that clustering is. Okay, there are multiple ways of doing it. One simple measure is by looking at the sum of squares. Okay, so like within sum of squares, it's actually a value. If you can see fit within sum of squares, it's 2 values because we have 2 clusters. Okay, for each cluster, it tells me the distortion. Okay, remember the distortion that we defined here, right? So this one. This is the value that is shown as within sum of squares. That means within the cluster, what is my sum of all distances? Okay, that's within sum of squares. Since we have for each k, for each center, we have a value of within sum of squares. Since in this particular case we have k equal to 2, so we have 2 sum of squares. So if I take all the data points in the first cluster and compute the distance with its center, which is this point, and sum all those distances up, I get this value. Okay. Similarly, I take all the data points with cluster number 2 and take the distance with its center, which is this point, and take the sum, then I get this value. Okay. This is the most important metric that is kind of used as an indicator to signify how good your clustering is. Okay. Obviously, as you can imagine, as you proceed to more and more iterations, your within sum of squares kind of should decrease, right? Initially, you started with some random centers, so your within sum of squares would be very large. It's not optimal. And as you update your cluster centers and proceed in your k-means algorithm, your within sum of squares kind of reduces and kind of saturates at some point. And the point at which it saturates is the place where you want to stop. Okay, so I did not specify the number of iterations when I run k-means, right? That means the default is iter.max is equal to 2. So let's see, let's specify that value. Okay, let's say only 2. Okay, now I see fit within SS. Actually, okay, it converged after first iteration itself because it's a very, very well defined structure. But if you have random points, then you can see your within sum of squares kind of goes down. Okay, any questions so far? Okay. Okay. So now let's go to the question of okay, usually how many iterations are needed? Nobody can answer that. It's totally depends on the data. Okay, you try with some number and then you look at the structure, or you look at your result and then you try it again. Or typically you don't just rely on number of iterations, but also rely on whether your cluster centers are updating or not. Okay. So from iteration to iteration, if your cluster centers are not moving very much, then you kind of say, okay, we have a good clustering arrangement and I'll stop it here. Okay, I typically in my applications use 100 and yeah, around 100 typically. I start with that. Yes, Mohan, I'm getting to that point. Visually, we can see that 5 clusters, but I just started with 2. I'll show you, yeah, I'll get to that point in a minute. Okay, before that, let's actually create, let me open one file just so that it's easy to, this is a code I am going to share in the LMS, so don't worry. I just wrote down 2 functions to kind of measure the, so we said within sum of squares is the way with which you can kind of measure the quality of clustering, right? So obviously we can sum it up and then make it a total distortion measure that we computed here, right? Which is a sum over all the within sum of squares. Okay, so I just wrote a function that computes the distortion. Okay, so this is function to compute distortion. Okay, so it takes a data set, it takes a k, the number of centers, it computes the k-means clustering for that centers, and then it simply sums up all the within sum of squares and returns. Okay. So Sanchit, just hold on to that question. Hopefully this will answer. Okay, so let's define this function. Okay, this function is essentially takes a data set, takes number of centers and returns the within sum of squares. Okay, now the first question that every one of you are answering is why only 2 clusters? How do I know the number of clusters and so on, right? Typically you don't know. I mean, this is a simplest example in 2-dimensional space. So I plotted it and I can look at it and say, oh, okay, I have 4 clusters or 5 clusters and so on. But in your real data sets, you will have a number of dimensions. I mean, typically you will have hundreds and in hundreds, and in the worst case you can get even thousands of features, right? Obviously you cannot visualize. Even if you go to 3-dimensional space or 4-dimensional space, we can't visualize it right away, right? So, and therefore you cannot just look at the data and say, oh, okay, I try with k equal to 5. You cannot do that. So typically you try with different k, and then you see what is the best value that you can get. Okay, you plot your distortion for different k's, and then you kind of see what is your best value of k. Okay, that's what I'm going to do now. Okay, by essentially what I'm trying to do is I want to invoke this function k-means dot within sum of squares for a given key k, with d equal to 2, d equal to 3, d equal to 4, d equal to 5, 6, 7, 8, and so on. Okay, I run so many times. I'll take the distortion value and I plot it. Okay, and instead of running this command 10 different times, I'm using a function called sapply. Okay, this is a R function with which you can kind of apply the same function but for different values again and again. Okay, so if you look at the help of sapply, there are many variants of apply, but the one that we are looking at now is a supply. It takes a function, it takes a data value, a bunch of data points, and then it applies that function on these values again and again, one after the other. Okay, instead of writing this function 10 different times, I'll simply say sapply of 1:10 and my function. Okay, so essentially this function is executed 10 times, once with 1 and then with 2, then with 3 and so on. Okay, and in this particular case, we want to vary the number of clusters k. Okay, so I write something like this. Okay, sapply k equal to 2 to k equal to 15. Those are the values that I'm going to try out, k values. And then for each of those, I want to execute my distortion function that I just wrote. Okay, and then there is also the second parameter, which is kind of constant across all the invocations, right? We are only varying k. The constant parameter is specified here, k equal to whatever is your data data set. And then by simplify equal to true, I'm just getting the list of results as a simple array. Okay, so okay, since it takes data, let me just define data to be d. Okay, remember d is our point, d is our data, right? Plot of data will be this again, obviously. Now okay, actually let me just define this function, which basically tries out all different k's and gets the within sum of squares. Okay, now if I say WSS is equal to k means dot WSS of my data. Okay, so I get bunch of values. This is k equal to 1. That means I don't do any clustering. Everything is one cluster. Or I have 2 clusters, 3 clusters, 4 clusters, and so on. Now I can plot this. Okay. Let's plot with lines. That way it's a little clear. Okay. B means both, means I want points as well as lines. Okay, that's just an argument to plot. You can see it from plot. Here, if I say P, I just get the points. If I say L, I get the line, and B means both points and lines. Okay, so for example, if I say L, I just get the line plot, and if I say B, I get both points and this thing. Okay, from this thing, now I can see that, oh, okay, maybe around cluster k equal to 5, I kind of getting good result. So I look at this plot and say, okay, for this data, k equal to 5 is the most appropriate one. Okay, that's how you go to find out the number of clusters in your data. Okay, is that clear, everyone? Yeah. Okay, so that's exactly goes to the Yeah, this method. So this is typically called as a elbow method. Okay, you just try out different number of clusters and your objective function, which is your distortion value. You plot it and you kind of look at the knee of the curve, which is where your number of clusters, you decide number of clusters. Okay. And there are other variants of it also. There's BIC, Bayesian information content, that you compute instead of distortion. You compute this quantity and then plot it and look at it. There are many variants of it, but just plotting the distortion should be good enough in practice. Okay. Okay, this is a next question which typically we have in our mind, right? Okay, this method seems good and easy, but do we get the best solution? Do we get the optimal solution? And the answer is not necessarily. Okay, like the one you've seen in on our slides before. Here, for k equal to 4, this may not be the best answer, right? Actually, I can construct an answer where k, this is one cluster, this is one cluster, this is another cluster, and this is another cluster. Okay, that seems a little more natural than forcing two clusters in this close proximity, right? As I think one of you already said, my pink and brown are so close to each other. Is this really a good result? Okay, so you can see that you may not get the best result always. Okay, and that's because of this notion of local minimum and global minimum. Okay, and the way to understand that is, let's go to my paint again. So remember, we have this objective function called distortion, right? This is our objective function, and this is what we want to optimize for it. Okay, we want to find the smallest value for this distortion. Now, if I look at the complete space of values, space of solutions, okay, this is my space of solutions, and if I plot the value of my objective, it will be some complicated function, right? This is my distortion, and depending on the point solution, I have different distortion. Okay, now I want to find a point that is lowest. Okay, so I want to find this particular point. This is my solution, because that is the point where my distortion reaches the minimum value. Okay, however, as you can see, there are so many other these small little minimum points, right? These are all kind of minimum in their local context, but that's not the minimum in the global context. Okay, so this is a global minimum across the entire spectrum of solutions. This is the best result that we are looking for. However, a lot of times you will get stuck in this local minimum. This is just the way math operates. This is just the way optimization functions get optimized. And a lot of times you get stuck in this point and think that, oh, okay, if I try here, I'm not really reaching a best value. If I try here, I'm not reaching a best value. So I think that, oh, I'm in the right place and this is the solution I'm getting it. Okay. So once you reach here, there's no way you can, mathematically, you cannot escape from this and go here, right? So your solution will get stuck here and you think this is your answer. Okay. And that is the reason why you may not get the best answer always. Okay. That's because you are essentially getting stuck in your local minimas. Okay, this is exactly showing that particular scenario pictorially. If I have these points and if I want to divide into 3 clusters, then my obvious solution would be one cluster here, two cluster here, third cluster here, right? But if I run my algorithm, depending on where I start, I can get answer like this as well. This is one cluster, second cluster, and third cluster. Okay. So mathematically, I get stuck in my local minimum, which may not be my global minimum. Okay. That's why it's not necessary that you find your optimal solution always, unless you do something about it. Okay. Any question so far? Okay. So let's see what we can do to get optimal solution, or at least get closer to optimal solution. The first thing that we can try is, so remember our method. The first thing that we did in our method is start with some random starting centers, right? We started completely random in our data, so we don't really know where we started. And so if I go here, let's say I start here, okay, this is my starting point. Then if I optimize, obviously I'll go to this point. And if I start here, I'll go to probably this point because this is minimum than this one. So I go to the closest minimum, which is here. So depending on my starting point, I'm getting closer to one of the solutions, which may be local minimum, right? So the starting point plays a very, very important role in determining where your solution converges to. Okay. So one obvious thing that I can try is try many different starting points, not just one point, but many different points, and then try for all of those different starting points and choose the best one. Okay, that's one method. Or even better method is by careful selection of starting point. Instead of choosing randomly, I choose one particular method is this. I choose the first center at random, okay, not all k centers, but first center at random, and then choose the second center that is as far away as possible, okay, and then similarly choose the third center that is farther than these two. So basically I'm spacing out my k centers as far as possible, so that I won't start with a solution like this. Okay. By spacing out as far as possible, I'm giving kind of enough room for the algorithm to discover the better solution. Okay. That's one heuristic that you can apply in practice in order to find better centers. Okay. And the other thing that we already talked about is start with different random points. Okay. These are all different heuristics. They do not guarantee the optimal solution, but at least they increase the chance of getting to the optimal solution. Okay. And we already saw how to find the number of clusters once we know how to start at different points. Okay, any questions so far? Is that clear, everyone? Now I hope all your kind of concerns got answered. Okay, great. And apart from the number of clusters and number of iterations and all those things, a couple of other important things that you need to remember for running k-means is the starting point, obviously, where to start. And so we talked mostly about the continuous data points where we are taking points from n-dimensional space. But a lot of times you may have some categorical attributes as well. Okay, we talked about what is a categorical attribute, right? Something like shoe size or shirt size, small, medium, large, or gender, male and female, right? How do I compute the distance between male and female? I can't really do Euclidean distance there, right? Then you come up with different similarities which are geared towards categorical attributes like Jacquard similarity and Hamming distance and so on. Okay. Again, depending on the data, you try different distance measure. Okay. Or other way to handle categorical attribute is something called as dummy coding. Okay. If I have, let's say, data to be male, female, male, female, male, female, female, male, and so on, right? This is my gender attribute in my data. Okay. Now I can convert these categorical attribute into two columns. One is gender.m and then gender.f. Okay. Gender.m will have 1 wherever there is a male. So this would be 1, 0, 1, 0, 0, 1. And then female is again wherever there is a female value, I will put 1. Okay, so there will be 1 and then 0, 1, 1, 0. Okay, so this is one way of converting a categorical attribute into a Boolean or a 0, 1 attribute. And once you compute this, you can kind of run k-means, right? Because if I do Euclidean distance between two different data points, if both are males, then my distance will be 0, which is kind of what we want, right? Both are similar, so my distance is 0. And if I am computing the distance between first record and the second record, then my distance will be 1, which is again kind of meaningful because both are different values of gender, and therefore you get a distance greater than 0. Okay, so this is called something called as dummy coding. This is one way of handling categorical attributes. Okay, one of the many ways, but one popular way. Now, this is also something that you need to remember when you have data which has categorical attributes in it. Okay. And similarly, I think one of you mentioned about different units of measure, right? What do I do? I can do normalization, which is taking the sum of all the coordinates and then divide. Or other thing is also called as standardization. That means you bring all of them, all the attributes into the same 0 to 1 range. Okay. Let's say my data has 3 columns, my income and the distance in kilometers and let's say age. Okay. And the range of values and the magnitude of values for these 3 columns are completely different, right? My distance to my office location is maybe between 0 to 50, depending on how many kilometers I travel or how many miles I travel. And the income is again in thousands, right? Whereas age is typically between, if I am talking about employee database, it's typically between 20 and 60, right? Now, how do I account for the different magnitudes and different units of measure? One, we said normalization, which is row-wise processing, and standardization is a column-wise processing. Okay, so I compute the mean and the variance or standard deviation of all my columns, and then I do x minus mu by sigma. Okay, from every data point, I take out the mean and divide it by standard deviation. And if I do that, every column will then have values between 0 and 1. So they kind of all forced into a unified measure. And then I can apply my algorithms. That's, again, one more technique that you can apply in order to make some meaningful conclusions out of your k-means. Okay, and similarly, if you have outliers, okay, outlier is something that is way far away from your normal data. Okay, so if I go back to my picture, okay, let's say this is my data, and there is some data point which is far away here. Okay, there's only one data point. Now, when I say k equal to 3, how should I do k equal to 3? One possible approach is, this is one cluster, this is all one cluster, and this one point is the third cluster. Okay, that's possible, right? Because this guy is far away from each other, so maybe it deserves to be in its own cluster, while respecting intra-cluster similarity and inter-cluster similarity. But however, we don't want such one point to be forcing my cluster, right? And that's exactly the notion of outliers. So outliers are something that are far away from your regular data. So you want to handle those outliers before you do any clustering, okay? Or at least you need to remember and acknowledge the fact that outliers can spoil your clustering arrangement. Okay, and there are many ways of dealing with outliers. Like one simple way is just looking at the mean and standard deviation. So, for example, let me plot it again. Oops, why can't I? Oh. Okay, so let's say if I have age attribute, right? Let's say all my employees are between 20 and 40, but there are a couple of employees who are elder than typical employee size, let's say 50 years old or 55 years old. Now, we don't want our clustering arrangement to be distorted by a couple of those employees, right? How can we detect that? So let's say we plot all our employee ages and we get something like a normal distribution, right? Let me draw it in a better manner. Okay, we get something like that. Okay, one way to define an outlier is, so this is my mean, okay, my mean, this denoted as mu, okay, and also I have a standard deviation, okay, which is something like this, a distance. Okay, this is my standard deviation denoted as sigma. Okay, now one way to define my outlier is any point beyond 5 sigmas. Okay, from mu I take 5 times the sigma. Okay, this is my standard deviation that I can compute from my data, and this is the mu that I can compute from the data. Now I take 5 times the sigma, so that means I'm looking at somewhere here, right? And then similarly on this side, 5 sigma is somewhere here, okay? Anything beyond this is considered as an outlier. So this is all outlier and this is all outlier. Now, if this is my age, probably the employees with age 55 or close to 60 will be somewhere here. And that's how you can kind of determine what is your outlier. You can remove those data points and then run your k-means analysis on rest of the data points. Okay, that's one way of dealing with outliers. But the important thing I'm trying to say in all this, in this entire slide, is you need to kind of take some precautions before you apply k-means on any data. Okay? Any questions? I had a couple of other examples showing, like I had this data set, which I got it online. I'll show you where I got it from. It's essentially, actually let me go back to that data set. So this is a repository, data repository, which is used very, very commonly across different industries, academia, everywhere. People use this machine learning repository from UCI, University of Chicago. University of California, Irvine. So this is a machine learning repository. There are a bunch of real data sets that you can get from there. You can get data sets for classification, clustering, collaboration, filtering, and whatnot. Many different algorithms you can get data set from. And one of the data set I thought I would show you in clustering is this wholesale customer data set, which is essentially a data set produced by somebody in Portugal. It essentially has these features. Okay, fresh is the annual spending on fresh products, and milk is the annual spending on milk products. Grocery is the annual spending on grocery products, and so on. And then this is divided according to the region, different places in Portugal, Lisbon, Porto, and all the others. Okay, this is, yeah, that's the data. And I can just dummily, I can create this data set, read it into my R, and then run clustering on it. I can get some results, may not be completely meaningful because these two attributes, channel and region, are kind of categorical attributes, right? As we saw here, my region is something that denotes the location of these customers, okay? Lisbon, Porto, or something else. So before I apply k-means, I have to actually dummy code them, make it region dot Lisbon, and then region dot Porto, and then region dot other. Okay, if I do that, then I can get even more meaningful clustering results. Okay. Okay, any questions until this point? So Sanchit actually asked an excellent question. If outliers can distort my cluster assignment, shouldn't our selection of number of k clusters using our elbow method be able to handle it? Very, very good point. And yes, you can handle it that way also. Actually, I mean, I didn't say, I thought it will confuse you people more, which is you can use clustering to find outliers. Okay. Like imagine my data again here, and let's say I have a bunch of points here which are kind of outliers. Now I plot my elbow method by trying out k equal to 1, 2, 3, 4, 5, 6, and so on. Okay. Now obviously for k equal to 4, I might get kind of the knee of the curve. Right? This is one cluster, second cluster, third cluster, and all my outliers will be in the third cluster, okay, or the fourth cluster. Now then I can take a look at my cluster arrangement and say that, oh, okay, these guys are very, very far from each other, that I can compute from my sum of squares, within sum of squares and between sum of squares and so on. By looking at those numbers, I can say this is my fourth cluster, which is kind of seems like an outliers. So I remove all that fourth cluster and then focus on my rest of the data. Okay. So while outliers can distort your clustering arrangements, you can use clustering to find outliers as well. Okay. Is that kind of clear? I thought of mentioning that before, but I was afraid it might confuse you people. But now that Sanchit raised that point, I hope that's clear. Okay, any other questions? Yes, Sanjay, outliers will have a negative impact, but assume that you tried with all possible cluster centers, I mean, many random starting points and so on. So you can kind of isolate those clusters depending on how far they are. If they are kind of close to your rest of the data, then yes, then you cannot use clustering to identify them because you will just get screwed by those outliers. But if they're kind of far away and they're clearly distinguishable, then clustering should be able to find those distinguishing set of points. Even mathematically, it will not be hard if they are nicely distinguishable. And if you try many different cluster centers and random starting points, then you should be able to isolate those points as a different cluster. Okay, so actually in practice, I mean, clustering people do apply to identify outliers, but as you're raising your concerns, you may or may not find always, depending on the notion of outlier that is present in the data. If they find it, well and good. If they don't find it, they go to a different method. Okay, and other way to identify outliers in a simplest manner is by doing this, which is very simple, right? You just compute mean, standard deviation, and then look at points that are far away from your mean. That kind of gives you a sense of what an outlier will be. Yes, so this is one way as well, but see, this is focusing on one dimension at a time, whereas clustering is focusing on all dimensions at the same time. So there's kind of plus and minus to each method, and again there's some methods where you will use this, in some cases you will use the other one. It's all kind of depends on your data. So the pre-work for tomorrow class, actually more than pre-work, I would like you guys to just play with k-means and come back if you have any questions. If you want to do pre-work, you can kind of read about document clustering. Thank you and see you tomorrow. Bye.